What is radius of gyration? To understand radius of gyration, we need to understand what moment of inertia is, which is denoted by I. Now, about this concept we have already covered in last video, and if I simply summarize it, moment of inertia can be understood as resistance against the motion, or resistance against the moment, and we can also understand it as resisting bending and twisting caused by the moment or the rotational force. Right? Now, this is a simple explanation of moment of inertia. Coming back to radius of gyration. To understand radius of gyration, let us take this in the figure here. Let us take one solid circular disc. This here is a solid circular disc. Let us say that it is rotating continuously via this axis, x-axis. Okay, and now when this is rotating for a point mass, let us say that whole of this solid circular disc has mass m. Okay, and now I want to take certain point. Let us say I want to take a point here, and when I take a point here, let us consider that there is a mass m here. Now, for a point mass, the rotational force depends on both the mass and the distance, and this distance from the axis of rotation, from this axis of rotation, by the relation I equals to mr square. By this equation mr square, it means that when my disc is rotating from this axis and I'm taking a certain point mass, and now when it is rotating from this point axis of rotation to this point mass, I have a distance r, which here r is the radius of this circular disc. Right? Now, when it is rotating, this rotational force depends upon this distance and the mass, this point mass. Right? So from here I get the relation I equals to mr square. So for this whole of this solid circular disc, my moment of inertia will be equal to I equals to mr square, where I is the moment of inertia, m is the mass, and r is the radius or the distance from this axis of rotation to the point mass. Right? So if I look in the second diagram here, my radius r, which is this distance from axis to the point mass, can also be written as k, where k is the radius of gyration. Now if I substitute r with k, I'll have I equals to m k square. Right? Now for this mass, for m, I can substitute m mass. This mass will have certain area, so this mass can be substituted as area of that mass, I equals to ak square. Right? So this here can be a general explanation for moment of inertia, right, which we have covered last class. Now from here my radius of gyration k will be equal to root over of I by a. So this here is a general formula for radius of gyration. Okay, now if I want to find radius of gyration about this axis, about my x axis, so my radius of gyration along this axis, which is x axis, will be equal to root over of I x, which is moment of inertia about x axis, divided by area. So I'll have this. Now if I want to find my moment of inertia about the other axis, which is y axis, let us say this is y axis, so my radius of gyration about this y axis will be equal to root over of I y divided by area, right? So in general, what do I have? My k here is radius of gyration, and I here is moment of inertia, and a is the area of the section. I hope this simple explanation of radius of gyration is clear to you. The next topic for today is moment of inertia of some geometrical plane figures of different lamina. Now in this topic, I'll be showing you some of the moment of inertia for different geometrical plane figures, such as rectangular sections, hollow rectangular sections, triangular sections, circular sections, hollow circular sections, and so on. So before we go into this, I would like you to understand centroid. I would like you to understand what centroid means. So to understand centroid, I'll just simply show you a diagram. I have a diagram here. Let us say that this is a square, and let us say that it is running through the planes x axis and y axis. Now this plane where the two planes are coinciding to each other here is known as a centroid, which is denoted by G, or it can also be denoted by as CG. So my centroidal axis along x axis will be equal to Ix, or I can also denote it as Ig, and my moment of inertia about y axis, about the centroidal axis, will be equal to Iyy equals to Ig again. So this is the simple meaning of centroid. It means that where the two axes are coinciding, or where they are running crossing each other, that point is known as the centroidal axis, or the centroid of this plane. Now let us go with moment of inertia of different sections. First one, moment of inertia of rectangular section. Okay, for this I'll take a rectangular section. Let us say that x axis is running from here, and my y axis is running from here, okay, and this point here is my centroid G. Now let me say that this length of my rectangular section here is width B, and this is my depth of the section D. Now if I exactly point this distance from here to here, it is B by 2, and if I say this distance from here to here, it is D by 2. Now what will be my moment of inertia about x-axis for this rectangular section? So it is gonna be I x will be equal to, now I'm finding moment of inertia of this rectangular section about x-axis, which will be equal to BD cube by 12. And next I want to find moment of inertia about y axis. Now I'm trying to find it through this axis, which is y axis. So from y I have the depth d running for this rectangular section. So my moment of inertia about y axis will be db cube by 12. So this is my moment of inertia of the rectangular section. Now similarly, let's look at another one. Number 2, moment of inertia of hollow rectangular section. Let me clarify here that in this I'm not showing you any of the derivations. I'm just directly showing you the final formulas to find moment of inertia for different sections, so that you can directly use it to find the moment of inertia of the different sections. Okay, now if I say hollow rectangular section, for my hollow rectangular section, let me first draw the figure. Hollow means there is a hole in the rectangular section. Okay, so this is my hollow rectangular section. Let's say that only this part is solid. Only this part is solid. Only this part is solid, and let us say that y-axis is running from here and x-axis is running from here. This means that in this portion here there is a hole. Okay, now let this be the outer rectangle, and let this width be capital B, and let this be the depth of the outer rectangle, and its depth be D. Now again similarly, let this be the width of the inner rectangle, and its width be B, and let this be the depth of inner rectangle, D. Okay, now from this axis I have exact half, which is B by 2 here, and from here I have the exact half for the outer rectangle, D by 2. Similarly, if I see here, from here to here, it is exactly half, which is D by 2, and again inside portion of B part, if I see from here to here, it is exactly half, B by 2. So I have this one here. Now if I try to find moment of inertia of x-axis, about x-axis, it will be equal to moment of inertia of outer rectangle minus the moment of inertia of inner rectangle. That means if I want to find moment of inertia about this x-axis, I have to find moment of inertia of this outer rectangle minus the moment of inertia of this inner rectangle. Then I get moment of inertia of hollow rectangular section about x-axis. Now let us see what will be the moment of inertia about my about this outer rectangle here. So for this outer rectangle, what do I have? I have capital B for width and capital D for its depth. So in the previous figure here, what did we find for a rectangular section? about I x axis, it is BD cube by 12, which is gonna remain same here for the outer rectangular. So I'll have BD cube by 12. So this is the moment of inertia for this outer rectangle minus the moment of inertia of this inner rectangle. Again, it's gonna be same. For inner rectangle, I have small d and small b. So it's gonna be small b d cube by 12, right? Which I can further write it as I x equals to 1 by 12. Since 1 by 12 is common in both, open the bracket, b d cube minus small bd cube for inner rectangle, bd cube. So this is your moment of inertia for a hollow rectangular section about I xx. Similarly, I want to find moment of inertia about I y y, which will be equal to, in the previous, for along I y y, what was the formula? It was db cube by 12. So similar, it's gonna be same here. For outer rectangle, it is capital D B cube by 12 minus, for inner rectangle, it is small d b cube by 12. So again, I can write this as I y is equals to 1 by 12 is common in both. So what is remaining? Remaining is d b cube minus small db cube of inner circle. So I have this formula. Altogether. So this is the two moment of inertia. First one for rectangular section, second one for hollow rectangle. Now the third section that we're gonna see is number 3. Number 3, moment of inertia of a triangular section. Triangular section. So let me draw the section first. Triangular section, and let it be A, B and C, and this point be the apex of the triangle. Let us say that x-axis is running from here, x-axis, and y-axis running from the mid of the apex, y-axis, and this point where both the axes are intersecting is my centroid G. Okay, and from this apex to the base, let it be my height of the triangle, and let this be from A to B, let it be base of the triangle. It is the base of the triangle. Now if I find moment of inertia about I x axis for this triangular section, it will be equal to B base of the triangle, B h cube by 36. Okay, and if we want to find the height of the centroid where it is exactly lying, we can find it as the base, the centroid of this triangular section lies at the height of h by 3 from the base. Now similarly, if I want to find the moment of inertia about base AB, so I write I base, moment of inertia about base, or I can also write moment of inertia about AB. My AB is my base, which it will be equal to BH cubed by 12. BH cubed by 12. Similarly, if I want to find the moment of inertia about its apex, let it be I apex. Moment of inertia about apex, A, P, E, X apex equals to BH cubed by 4. So these are the few of moment of inertia for a triangular section that you directly giving you these formulas. There is no derivation, directly giving you the formula so that you can directly use these formulas to solve the numericals. Now next, let us see the moment of inertia of isosceles triangle. Or equilateral triangle. Equilateral triangle about, we find it from only one axis, which is y axis. Okay, let me draw the equilateral triangle. I hope it will come out right. Okay, equilateral triangle, this is. And I have to find it from just y axis, and from here to here it should be exactly be b by 2, and from here to here again b by 2, and let this from this point apex to the base till here be the height of the triangle H. Now for this isosceles triangle, my moment of inertia I y will be equal to H, height of the triangle, B, base of the triangle, which B, this whole from here to here is my base B, HB cube by 48. It will be this much. So you directly remember this formula for a isosceles triangle. And now next I have moment of inertia of unsymmetrical triangle or irregular triangle. Moment of inertia of unsymmetrical triangle. Unsymmetrical triangle, or you can say it is irregular triangle. Unsymmetrical means all three sides are different. Okay, let me draw the unsymmetrical triangle. So all three sides are not same, they are all irregular, they are all different. So my moment, my y axis will pass from the apex y axis. Let this be A, B and C. Now for this triangle, also unsymmetrical triangle, my moment of inertia about I y will be equal to H. Now this, both the sides and the base, this is my total base. Now this length is not equal to this length, so let us say that this length here is A and this length here is B, because both of them are not equal. So my moment of inertia about Iyy, this axis Iyy, will be equal to HA cube by 12, height of the triangle H, A cube by 12 minus plus H B cube by 12 here. So this will be my moment of inertia of unsymmetrical triangle about YY axis. Now let us go the fourth one, moment of inertia of a solid circular section. Solid circular section. So for this, let me draw the diagram. I'm sorry for my bad diagrams. So let us say I-axis is moving, YY is moving from here, Iyy. Then axis, x-axis is passing from here. Okay. Now this is my centroid G, and half of this is the radius R, and total whole of this will have a diameter D from here to, let's say, here, right? This will be the total diameter of the circle. So similarly in here, from here to here, I have half of diameter, which is radius. So in both the section it is divided equally, running through x-axis and running through y-y axis. So my moment of inertia will be equal to Ixx. Moment of inertia about x-axis will be equal to moment of inertia of Iyy axis will be equal to moment of inertia G, we can signify as this also, and it will be equal to pi by 64 d raised to power square. So this will be your moment of inertia of a solid circular section. Similarly, if I go for moment of inertia, the fifth one, moment of inertia of a hollow circular section, hollow circular section. Let me draw the diagram first. Hollow, okay. Okay. Okay, this is the centroid. Let this be the centroid G, and let this be solid here. Solid. And whole of this will have a diameter D. This diameter D, let it be the diameter of outer circle, and the diameter of the inner circle, let it be small d. Now from here, if I want to find the moment of inertia, again it will be moment of inertia about Ixx axis will be equal to moment of inertia about YY axis will be equal to pi by 64 d raised to power 4, capital D for outer diameter of the circle, minus small d raised to power 4. Small d signifies the diameter of the inner smaller circle, d raised to power 4. So this will be my moment of inertia for a hollow rectangular section. Now, next one, if I show you the moment of inertia of a semicircular section. Moment of inertia of semicircular section. Semi means it is half of the circle, right? So let me draw the diagram first. Semi means only half of the circle. So this is my semicircular section, and let it be x axis here. Let this axis be running from here as y axis, and this point here is my centroid. Now to find the centroid, the height, this height for this semicircular section lies at a distance of 4r by 3 pi from the base. So at this height you will have a centroid for a semicircular section. Now if I want to find moment of inertia about axis for a semicircular section, it will be equal to 0.11 r raised to power 4. Since the distance, this distance here, if I say, it can be r half, and here also it can be r. So total you will have d, right? Or you can say it is d by 2, or here d by 2, you can say that, right? But this distance you cannot say exactly how much it is that is running from x-axis. So the distance here is 4r by 3 pi from the base here, right? So that's why we have a different moment of inertia for semicircular section. And similarly, my moment of inertia about Iyy will be equal to pi by 128 d raised to power 4. Or if you write it in terms of radius, it will be pi by 8 r raised to power 4. So you will get this 2 moment of inertia. And the last one, last geometrical section is quadrant circle of moment of inertia of quadrant circle. Moment of inertia of quadrant Q U A D R A quadrant circle, or it is a quarter circle. Let me draw the diagram. Quadrant circle means half of this semicircle. Half of this semicircle will be only this much. Let me draw the diagram. It will be equal to, the diagram will be this much. So my distance here will be the same, x-axis running from here, y-axis. Similarly, from the base, my centroid lies at the height of 4r by 3 pi, just like in semicircular section, 4r by 3 pi, right? And my moment of inertia about Ixx and Iyy will be same, because this distance and this distance here is now same. So it will be equal to 0.055 r raised to power 4. So this will be your moment of inertia about Ixx and Iyy for a quadrant circle.